For a long time, scientists have been pondering why humans are the only animals with chins. So far, their hypotheses have failed to hold up to rigorous scrutiny. The current consensus is that it serves no inherent benefit but emerged as a side effect of something else. This is something known as a spandrel. They don't know what that something else is though. In 2020, I came up with a take which confirms that it's a spandrel and explains what that something else might be, which I'm going to present now. However, a quick disclaimer, this video is merely speculative and not necessarily informative. Let's start by looking at some evolutionary changes. Over millions of years, the early hominids transformed from a quadrupedal posture to fully bipedal posture. Their neurocraniums evolved bigger and heavier, and the jaws, and by extension the entire facial skeleton, evolved smaller and lighter. The center of gravity of the skull therefore moved closer to the spine. The neutral posture of these early hominids was much more forward-leaning than that of contemporary humans. To understand the situation, we need to define three concepts. First, tensegrity. Tensegrity is a structural principle in which rigid compression elements are held together by a continuous network of tensile elements, forming what's called a floating compression. This principle has been observed to apply to many biological systems, such as the human organism. This natural application of tensegrity is known as biotensegrity. In a biological organism such as the human, the soft tissues, muscles, fascia, ligaments act as tensile elements and the bones act as compressive elements. Muscle tone and muscle pairs. The role of each muscle is twofold. They engage in constant passive contraction, resting muscle tone, to maintain posture and structural integrity. Then, whenever needed, they engage in active contraction to perform a function, such as chewing. As we can see, these two masticatory muscles shown here, masseter and temporalis, close the jaw in perpendicular directions. This is a synergistic pair. All muscles that cross a joint have an antagonistic pair that opposes its movement. In the case of these jaw-closing muscles, it would be the jaw-opening muscles, such as the digastric muscle. Wolff's law. In short, Wolff's law is a principle which states that bones will adapt and remodel in response to mechanical forces placed upon them. Bones will grow in mass and density where they're needed and stressed, and atrophy and be resorbed where they aren't needed or stressed. Next, let's lay out the foundations for the skull balancing mechanics by interpreting the craniocervical relationship as a first-class lever. Here we have the craniocervical junction of a chimpanzee, with the neutral posture being essentially a forward head posture, and a smaller facial skeleton to neurocranium ratio, which parallels the situation of prehistoric humans. The center of gravity is located quite far and far away from the atlas joint, which functions as the fulcrum. The skull sits in balance, suspended by the knuckle muscles, with the posterior muscular chain and the spine functioning essentially like a crane. With the modern human, the center of gravity is closer to the atlas, and because of the straightened neck posture, the knuckle muscles are now oriented forwards. This introduces a new problem, as the resultant force vector, the orientation of the balancing force, is now tilted backwards. What is now preventing the neurocranium from collapsing backwards? The muscles would somehow have to inflict a rotational force on the neurocranium. Let's find out how that happens. Let's map out the key tensile forces that hold the skull together along the sagittal plane. Nuchal. Knuckle, ligament, and various neck muscles are pulling the back of the skull downward towards the spine. Tongue. In proper oral posture, the tongue should rest against the roof of the mouth in a suction hole created by correct swallowing. This forms negative pressure between the tongue and the palate. Now, what kind of mechanical force does this produce? A suction hole inherently creates a pulling force akin to a suction cup. However, according to the principle of an elastic vacuum chamber, any closed compartment with elastic walls and an inwardly directed pressure gradient may cause positive pressure on the rigid structures in its lumen. The palate isn't uniform in rigidity. The hard palate tends to transition into the soft palate gradually. This forms a pressure gradient wherein the front of the palate is pushed more upward and the back of the palate is pulled downward. This creates a rotational force, a torque essentially. There's also a muscle called palatoglossus pulling the palate and the tongue towards each other, with fibers running towards the apex of the tongue. So here we have the torsional tongue effect, which the neurocranium reciprocates by rotating towards the palate. We already achieved some rotation there. Temporalis. This is where we get to the formation of the chin. Notice how the coronoid process is an angle towards the fibers of the temporalis but has some curvature to it. In other primates it is straighter. This is because in other primates there is no rotational force needed and the temporali are holding the skull together in a more linear fashion. So as the temporalis tugs on the coronoid process, this forms a kinetic chain that travels to the mandibular tip, the chin. The curvature creates leverage by which the entire neurocranium cranks itself forward. Let's visualize these forces by simulating a situation where the temporalis is disengaged and the neurocranium starts to collapse backwards. Then the temporalis reactivates. A tensile chain is formed which seeks to reach a stable equilibrium. The chin becomes an anchor point as the weight of the neurocranium is transmitted there and begins to protrude due to buildup of torsional energy. Next, let's visualize the leverage created by the curvature of the coronoid. Imagine that the temporalis does manage to pull the coronoid towards itself. Then it re-establishes the original curvature with the temporalis pulling on it. See how it affects the rotational force on the neurocranium and the chin. Finally, here's an overview of all the forces shown before. We can see how this creates a balanced structure wherein a hypothetical drift in any direction could be countered by an oppositional force. Here are some other muscular connections shown that I left out, like the hyoid bone and its various attachments. To conclude, only humans have chins due to the unique buildup of rotational energy at the mandibular tip. This is caused by the resting muscle tone of primarily the temporali, in order to prevent the neurocranium from collapsing backwards. This evolutionary adaptation is linked to changes in skull dimensions and the transition to fully upright bipedal posture.